Hello everyone and welcome back to tutorial 2 of MIE100 Dynamics at U of T. Our topic today is going to be about kinematics of particles, so stick around, and if you have any questions, make sure to drop a comment below. Okay, so let's start with problem 1 of the tutorial. We have an overhead view of part of a pinball game, and if the plunger imparts an initial speed of 3 meters per second to the ball at time is equal to 0, determine the acceleration A of the ball at time t is equal to 0.08 and t is equal to 0.2. Noting that at point F, the speed of the pinball has decreased by 10% from the initial value, and this decrease may be assumed to occur uniformly over the total distance traveled by the pinball. So r is 150 millimeters and theta is 60 degrees. So let's start with noting down all of our known values. We have VA is 3 meters per second, T naught is 0 seconds, VF is VF decreased by 10% from VA, so that's 90% of VA, or 0.9 times 3, which is 2.7 meters per second. We have R is 150 millimeters, or 0.15 meters, and theta is 60 degrees. So before we start solving, let's start with a little background to understand this problem better. So if we want to find the velocity for a constant acceleration, this is very important. The following equations are just going to be for a constant acceleration. But if you want to find the velocity, and we have here a graph of acceleration versus time. Now, if we take a little area under the graph here, this is going to be A, and this is going to be dt. Knowing that A multiplied by dt is the difference in velocity. Let's say it starts from v0 to v and from 0 to t. We'll have, after we integrate that, we can have v is equal to v0 plus at. Now, what if you want to know the distance? If we have a graph of velocity versus time, and we take the area under the graph, we're going to have v, and this is going to be dt. So v dt is going to be equal to the difference in distance, ds. So from s0 to s, and from 0 to t. Now, if we plug in this equation here into the integral, we can have ds is equal to v0 plus at multiplied by dt. And then once we integrate that, we can have s is equal to s0 plus v0 t plus half at squared. Now, if you want to solve these problems, you can just start with these equations over here. I'm just showing you how we found them in the first place. Now, what if we have a different graph? If we have acceleration multiplied by the distance, and we want to find the area under the graph here. So it's just going to be A, and this is going to be ds. From what we already know here, we can tell that ds is going to be v dt, and A is going to be dv over dt from this equation over here and this equation over here. When those two cancel each other out, it becomes v dv from v naught to v is equal to a ds from s naught to s. And once we integrate that, we can have v squared is equal to v naught squared plus 2a multiplied by s minus s naught. Now, this is the final equation for a constant acceleration. And those equations only work for a constant acceleration. But what if we have a curvilinear motion? With a curvilinear motion, the acceleration is not constant. The acceleration becomes two parts: the normal acceleration and the tangential acceleration. So we have a ball, and it's accelerating on a curve here. This is going to be at, which is the same as the direction of the velocity. And we're going to have an, which is pointing towards the center of the curve. Now, an is going to be v squared over r, and at is just going to be the integral of the velocity. Now that we have all the background information covered, let's actually start solving for the equation, for the problem, sorry. Let's go back here to the actual graph. Now, we want to find the total distance traveled by the pinball. To do that, we have how many r's? We have 1, 2, 3 r's. We have a quarter circle over here, the circumference of a quarter circle, and the circumference of another curve with the theta known and the r known. So the total distance, SAF, is going to be equal to 3r plus pi r over 2, which is the circumference of a quarter circle, and theta over 180 multiplied by pi r, which is the circumference of a portion of a circle. And now we just need to plug in what we know. So 3 times 0.15 plus pi multiplied by 0.15 over 2 plus 60 over 180 pi 0.15. And this is going to give us 0.843 meters. Now we want to find the acceleration along this whole distance, but we know that the acceleration is not linear, constant due to all these curves. So we want to find the AT portion, or the tangential portion of the acceleration. So we're going to use this equation over here to find the acceleration. So it's going to be VF squared equals to VA squared plus 2 AT SAF. We know that VF, we calculated it before, to be 2.7, and VA we know is 3. S we found out to be 0.843. So once we solve for that, we get AT is equal to minus 1.014 meters per second squared. Now that we have all the necessary values, we can start solving for part A. Now, part A, we know that T1 is 0.08 seconds, so at that time, What's the acceleration? So first of all, we want to know what the velocity was at time t1. So we're going to use this equation over here to solve for the velocity. So v1 is equal to va plus at t1. And when we plug in our known values, we get v1 is 2.92 meters per second. Now we want to know the distance traveled, the distance traveled during that time. We have the velocity, we have the acceleration. We just need to find the distance. So we're going to use this equation over here to find the distance traveled by the ball during this time. So we have S1 is going to be equal to SA plus VAT1 plus half AT1 squared. We plug in our known values. And we get S1 is 0.236 meters. Now if we go back to our graph, this is 0.15, and this over here is 0.2 something, the distance of this curve. So we know, that means that we know this distance is going to be within the first curve. This is where the ball is currently at 0.08 seconds. Knowing this information, we can now find out exactly where it is on the curve. So S1 is going to be equal to R plus theta over 180 pi r. We want to find theta to know exactly where it is on the curve. So 0.236, we're going to plug in our known values. And we're going to get theta is equal to 32.8 degrees. Sorry, let's not call it theta though, so we don't get confused. We already have a theta. We're going to call it phi. So now that we know exactly where our ball is, now we can find the normal acceleration. We know that v is 2.92 squared over 0.15. So our AN becomes 56.8 meters per second squared. Now that we have both the normal acceleration and the tangential acceleration, we can solve for the total acceleration. So this is our ball. This is the path that it's traveling towards. And this is B, this is C. This is AN. This is AT. Sorry. And this is phi. So we want to know the acceleration in terms of I and j, the I and j coordinates. So we're going to have minus an1 sine phi minus at1 cosine phi plus an1 cosine phi minus at1 sine phi. This is just basically trigonometry. So if we plug in the equation, if we plug in the known values that we have, we can get finally, after we plug in all those values and calculate for the acceleration, we can get minus 31.6 I plus 46.9 J meters per second. And this is the final answer for part A. For part B, we're just going to be doing exactly the same thing. We know that t2 is 0.2 seconds, and we want to know a2. So we're going to use the same exact method again. We're going to find the velocity first. We're going to plug in all of our known values. That's going to give us v2 is equal to 2.8 meters per second. We're going to plug that into the distance equation. Let me write it down again. And distance we get is 0.58 meters. Now, if we calculate the distance, we find that 0.58 meters lies within the second curve. So knowing that it lies within the second curve, we need to find out exactly where it is on the second curve. So 2r plus pi r over 2 plus phi 2 over 180 multiplied by pi r. Plugging in our known values. We're going to get phi 2 is equal to 16.95 degrees. Now that we have all of that, we can start solving for the acceleration. Actually, we can start solving for the normal without finding the phi. However, we will need phi once to calculate the total acceleration. So the normal is going to be 2.8 squared over 0.15, giving us 52.3 meters per second. This is the ball. And this is E. This is D. AT is going to be pointing this way. AN is going to be pointing this way. We know that this is phi 2. So to calculate the total acceleration, we have AN2 cosine phi 2 minus AT sine phi 2 in the I direction, plus minus AN2 sine phi 2 minus AT cosine phi 2 in the J direction, and then we just plug in our known values. And finally, we can get A2 is equal to 49.7I minus 15.5J meters per second squared. And this is the final answer for part B. So now for question 2 of the tutorial, we have the pulley system shown. Each of the cables at A and B is given a velocity of 2 meters per second in the direction of the arrow. Determine the upward velocity V of the load M. So first of all, we're going to write down our known values, which are VA and VB are equal to 2 meters per second. And we want to know the velocity in the upward direction, so y dot. So to solve this problem, we first need to know the lengths of the cables. So let's assume first that this distance over here is y1, and this distance over here is y2. This means that this distance over here will be y2 minus y1. Now in the x direction, from point A to the pulley, this is x1, and from point B to the pulley, this is x2. Now, we want to know the lengths of the cable. So, how long is this cable over here from point A? That's going to be x1 plus y1 plus y1 again equals to a constant. When we differentiate that, we get x dot 1 plus 2 y dot 1 equals to 0. Now, we rearrange this a little, we get y dot 1 is equal to minus x dot 1 over 2. Now we're going to do exactly the same thing with the cable in part B. So this is going to give us x2 plus y2 plus y2 minus y1 equals to a constant. And when we differentiate that, we get x dot 2 plus y dot 2 minus y dot 1 is 0. Now we already have the value for y dot 1 over here, so we can substitute this equation into here to get and when we substitute the values we have, VA and VB, we can get y dot 2 is equal to minus 1.5 meters per second, or 1.5 meters per second in the upwards direction. And this will be our final answer. Now, taking a look at problem 3, we have a baseball player releasing a ball with an initial velocity of 35 meters per second at an angle of 35 degrees with a horizontal line. So if t is equal to 0 is the time of release of the ball from the player's hand, determine the rate of change of the speed at t is equal to 1 second. So the rate of change of speed occurs along the line of the plane, so it's a tangential acceleration, using geometry to find the direction along the path. So let's start off with noting our known values. We know that V0 is 35 meters per second, theta is 35 degrees, and at t equals to 1 second, we want to know AT, the tangential acceleration. So first of all, let's analyze this on the horizontal plane. We know that the equation for distance is s equals to s0 plus v0 t plus half at squared. In the horizontal plane, s0 is 0, and there is no acceleration. So we have x is equal to v0 cosine theta t. Once we differentiate that, we get x dot is equal to v0 cosine theta, which is also equal to vx. Vertically, we're going to analyze it in the same way. We have y is equal to y0 plus v0 y t plus half gt squared. We know that y0 is equal to 0. So we're going to get, once we differentiate that, we're going to get y dot is equal to v0 sine theta minus gt is equal to vy. Now, at t is equal to 1 second, we can plug in the values we have into those equations. So we'll get vx is equal to 35 cosine 35 to get vx is equal to 28.67 meters per second. When we plug it into this equation, we get vy is equal to 35 sine 35 minus 9.81 multiplied by 1 to get vy is equal to 10.27 meters per second. Now let's draw a little diagram of what we have so far. We have vy pointing that way, vx pointing that way. That means the velocity is going to be pointing this way. The tangential acceleration is pointing in the opposite direction, due to gravity, and the normal acceleration will be pointing towards the point of curvature. So we want to know this angle over here. Let's call it phi. So phi is going to be equal to arctan Vy over Vx. When we substitute in the velocities, we get phi is equal to 19.7 degrees. Now, when we differentiate the velocities again to get the acceleration, Vx dot becomes 0, but Vy dot becomes minus 9.81 meters per second squared, or basically gravity. So if we go back to our little diagram, If we go back to our little diagram, this is going to be our AY, there's no AX, and this is going to be phi. So the tangential acceleration is just going to be minus AY sine phi in the j direction. So when we plug that in, we can get AT is equal to minus 3.31 meters per second squared. And that's our final answer. So for our last problem of the tutorial, we have a point mass located at x 10 and y 5 meters with respect to a given set of rectangular axes, following some information about its motion. So we want to find the speed of the particle, the velocity of the particle expressed in normal and tangential coordinates, the tangential acceleration, AT, and the radius of curvature of the particle's path, rho. And then we're going to sketch the direction of the normal velocity. So first of all, let's write down our known values. We have xy is 10 and 5 meters. X dot and y dot is minus 2 and 2 meters per squared. X double dot and y double dot are minus 2 and 1 meters per second squared. So before we start with the question, let's go through some background information. So first of all, what is the normal and tangential coordinate system? The normal and tangential coordinate system are expressed in En and Et. So imagine a point is traveling along a curve from A to A dash. The velocity at A is going to be split into two parts, the tangential and the normal. Tangential will be pointing in the same direction, while the normal is going to be perpendicular to the tangential, pointing towards the point of curvature. A dash will be exactly the same thing. Now the angle between A and A dash can be expressed as beta, and the distance between A and D dash can be expressed as S. The radius of curvature can be expressed as rho. So we know that S is equals to theta r, where theta is in radians. Therefore, we can say that ds is equal to rho dB, d beta. Therefore, if we want to find the velocity, it's equal to s dot, which is rho d beta over dt. The vector of the velocity is going to be equal to v et rho beta dot et, tangential unit vector. So this is one important equation that we need to remember. Now for the normal unit vector, it can be equal to det. Det is going to be equal to en multiplied by d beta, based on this equation over here, which can be simplified to et dot is equal to beta dot multiplied by en. This is another important equation we need to bear in mind. So for the acceleration, it's going to be equal to v dot, which is equal to v scalar multiplied by e dot t plus v dot et. We can substitute in this equation over here with this. Sorry. We can substitute this et with this equation over here to get v beta dot en plus v dot et. This can be substituted even further by substituting the beta dot with this equation over here, which would give us v squared over rho en plus v dot et. This is the final important equation we're going to need. Now, going back to the question, let's sketch out the point that was described. This point lies at 5 and 10. It's going at a positive y velocity and a negative x velocity, which means that the normal is pointing that way, and the tangential is pointing that way. So for part 1, the question is asking for the speed of the particle. So the first part of the question is pretty straightforward. It's just going to be equal to x dot squared plus y dot squared which is 2 squared plus 2 squared, giving us 2.83 meters per second. For the second part, the question is asking us for the velocity in the normal and tangential coordinates. So for this question, v is just going to be equal to et. This is because et is in the same direction as v, and en is perpendicular. Therefore, we get v, the vector velocity, is equal to 2.83 in the tangential unit vector, meter per second. Now for part 3 of the problem, we want to find the tangential acceleration. So to do that, we're going to draw two little graphs. Velocity. We want to know the angle over here, and another one of acceleration. We want to know the beta angle over here. So to find the angle, it's pretty simple. We're just going to use arctan y dot over x dot. Plug in the numbers we already have. To give us 45 degrees. For beta, we're going to do exactly the same thing, but with the accelerations. Plug in our values to get beta is equal to 26.6 degrees. After we get our angles, now we can solve for AT, which is equal to x double dot squared plus y double dot squared cosine phi. Now, where phi is equal to this angle over here. Knowing that this is alpha and this is beta, phi is going to be alpha minus beta. So once we plug in the equations, the values, we can get 45 minus 26.6, giving us AT is equal to 2.12 meters per second squared. Now for part 4, we want to find out the radius of curvature. So to find that out, we first need to know the normal acceleration, which is equal to v squared over rho. This can be expressed as x double dot squared plus y double dot squared sine phi, or alpha minus beta. Once we plug in those equations, we get an is equal to 0.71 meters per second squared. So once we plug it back into this equation, we get 0.71 is equal to 2.83 squared over rho. Now we can solve for rho to get 11.35 meters. Now for the last part of our problem, we want to sketch En. Since we've already had a lot of sketches, this part's going to be fairly simple. These are x and y coordinates. This would be the direction of ET, same direction as the velocity vector, with angle alpha, or 45 degrees. And the normal is just going to be perpendicular to that, which means this is also going to be alpha, or 45 degrees. So that was the end of our tutorial. Thank you so much for sticking around. And if you have any questions, drop a comment below or email me on noor.doidar@mail.utoronto.ca. Have a nice weekend and see you next week.